All right, let's look at a simple example of behavioral Verilog. So there's a module up here, it's 5 lines. It's basically one assignment statement. And it says assign x equals, and it has this ternary operator, a equals b, and it wants to set x equal to either a 1 or a 0. So block diagram. Right, so A and B are one bit inputs, and x is equal to 1 if A is the same as B, and it's 0 otherwise. And we can specify that we want a circuit that does this with this single line of code. Well, that's not terribly surprising because this is really just an exclusive NOR gate. Right, if you take A and B and you put it through an XNOR, it will give you a 1 if A and B are equal to each other and a 0 otherwise. So that's not really surprising, but we can actually create vectors that represent things with more than 1 bit. So here's what I can do. I can say let's make a module called equal, ABX. A and B are inputs, X is an output. And suppose I want to compare 8-bit numbers, A and B. So I can write a statement called wire, which says that A should be a wire. And by putting bracket 7:0, I'm saying I want this to be actually a collection of 8 wires. It's like an array in C. So it contains an A0 and A1 all the way up through A7. So I'm making basically an array of wires. What we call in digital logic a bus. So A is actually 8 wires, and we can think of this as A bracket 0 through A bracket 7. So now, just by adding this one line, I've defined my system diagram to look like this. There's 8 lines coming in for A, 8 lines coming in for B. And I can use that same assignment statement but here I'm asking it to compare an 8-bit number to another 8-bit number. And if they're equal, set x equal to 1, otherwise set x equal to 0. And this will synthesize. Okay, not terribly hard still. It's really 8 exclusive NOR gates. And then you take the outputs and you put them through an AND, I think. And if each bit is equal to each bit between A and B, then A and B are equal to each other. But I could also do something like, if A is less than B, set the output to 1, otherwise set it equal to 0. And now to do that, it's got to do some kind of subtraction operation with A and B and see if the result is negative or not. And that'll synthesize. It'll figure out the circuitry to do that. So in that handout, there's another example here. This is a 2-bit adder. This is lab 4. And it's 6 lines of code in Verilog. So I put the bracket 1:0 on input instead of wire. There's options here. But basically it's a module that takes in 2 inputs A and B and generates an output sum. A and B are 2-bit inputs because I set them up as arrays going from 1 to 0. And S is a 3-bit output. And then this one statement, assign S equals A plus B, that plus means addition. Okay, for ORing in programming languages in Verilog, we use a pipe symbol. Okay, and is still an ampersand. A plus means addition. So this says I want to take A and B, treat them as 2-bit numbers, add them together, and take that sum and assign it to S. That's a 2-bit adder. And that will do everything that you did when you did Lab 4. It will figure out half adder, full adder. It will come up with equations for those, minimize them. It'll do little gate maps in its brain, and it will convert it into a bunch of gates and inverters and wires and come up with the information to build that circuit.
So when you have the brackets and the inputs, when they're in the same line, it just means that it's already initializing the wire?
It means it's a bus. It means A is not a single wire, it's actually 2 wires in this case.
Okay, gotcha.
And S is 3. And if I want to refer to them, I could do A bracket 0 or A bracket 1, because I started from 0. All right, so that plus sign is dynamite. So that's as far as we're going with Verilog for today, so let's play with it. Because that's always more fun. So the lab says a lot of stuff. So what are you doing in the lab? You're making an AND gate, and I actually give you the Verilog code for that, so it's really about learning the tool. This is kind of ugly. That's okay, we'll deal with it. Then experiment 2, you're going to do the same thing, but you write the code yourself for a 2-input multiplexer. Then experiment 3, you implement a state machine for the mood machine. Right, so very happy, happy, sad, and very sad. And you're going to design this. So we'll have to talk about this, but the beginning of this lab talks about the details of how you actually take a Verilog program, compile it, execute it, and look at the results of the simulation. And so it starts off with telling you that there's these magical flash drives in the collaboratorium labeled Icarus Verilog that contain all the necessary software. It's not true. I never made the flash drive. Because I got the Verilog software installed directly on the machines in the collaboratorium. Okay, so you don't have to put it on a flash drive. And in the collaboratorium, so how many people here like DOS? Because you're going to have to work in DOS for this, because that's the only option on Windows to do command line stuff. So there's still things you can only do in DOS, I believe. So C:\\/ I think it's called / Icarus. So here's my next really important comment, right? I will be in the lab tomorrow morning at 9 o'clock. Well, I'll be in my office right next to the lab. Tomorrow from 9 to 10 and from 11 to 12. You want to make sure that by the time 12 o'clock comes tomorrow, you have figured out how to compile Verilog programs. Don't have to know Verilog yet, okay? But you want to be past the hurdle of, I'm going to write Verilog into a text file. How am I going to compile it? How am I going to simulate it? Okay? Which means either figuring out how to do this on the machines in the collaboratorium or downloading the software yourself onto your own equipment and making sure you can run it. So I'll show you where to download it in a second. But get through one of those hurdles by 12 o'clock tomorrow, okay? And I'll be in the lab 2 hours, right, 9 o'clock and 11 o'clock. And you can also come in here at 10 if you really can't find me any other time, because Fridays at 10 is an open lab in here. But don't blow this off and then on Sunday send an email saying, like, I have no idea how to run Icarus Verilog, because it's really hard to do over email, okay? And it's really easy to do if we're sitting down in front of whatever equipment you're trying to do this on. So please try to do this today and let me help you with it tomorrow if it doesn't make sense. So on the collaboratorium, it's either called Icarus or Icarus Verilog. I got to double check. But basically, you can do everything we're going to do by just saying C:\/ Icarus / and then the commands we're going to use: iVerilog, VVP, GTK Wave. And I asked them to set up the path to do this automatically, but it didn't take for some reason. So you got to specify it yourself. But your other option, and this is your better option, is to install this on your own equipment. Now your best option in life is always to run Linux. And if you're running Linux, you can just install this and it works great from the command line. If you're running Windows, we got to find where you do this for Windows, and it's a weird site. But it is the correct site. And then we've got a pokey connection. Give me 1 minute and I'll give up. There we go. All right, so blyer.org/Icarus. And find the right version for Windows, either 64-bit or 32-bit. And download it and just go through the usual setup. And it doesn't like spread its tendrils into thousands of places on your machine. It's really just a directory with files in it. Yeah?
Are the computers on the Cloudtorium 64 or 32?
They're 64,
Okay.
as far as I know. And like I say, the software is already installed in there, but the path doesn't point to it.
Can you do it in Linux?
Oh, in Linux, I think you can install it from the Software Center,
Oh, okay.
like the Discover tool or whatever it is on your
Yeah.
system.
Okay.
And then it just sort of drops into your life, and it's glorious. All right, so I'm on Linux, and I've already got this installed, so let's just play with it. All right. So these are comments in the top right. This is how we're going to compile a Verilog module. This is how we're going to execute it. This is how we're going to look at the output graphically. Okay, so I just put those as comments in the beginning. So we're making a module. I just call it a test bed because it's just a test thing. And what we're building here is an AND gate. Okay, it's kind of like a hello world, simple test. So module test bed. I have two inputs, and I'm calling these registers because here's the thing. If I say module test bed in1, in2, comma out, input in1, in2, output out, assign out equals in1 and in2 and module, right? That will design an AND gate, but we can't do anything with it. I compile it, and it'll compile it and say, okay, I compiled it. But we don't have any way with that to actually see what it does, to actually confirm that it works as an AND gate. Okay? So we need to move towards what we call a test bench or a test bed. And a test bench is a way to take a module we've developed and say what we want to do with the inputs, what we want to do with the outputs. It's basically hooking up switches and LEDs, but the software version of these. Okay, since we're trying to give values to the inputs, we want to do something like, say, for example, input 1 is assigned a value of 0. Or input 1 is assigned a value of 1, or input 2 is assigned a value of 1. And we can't do that with a wire. We can't say, I want this wire to be assigned to a 0, because that's going to connect it to ground, right? And that's not what we want. So instead of calling these things wires, we call them registers. So we say register N1, register N2. Register basically means that when we give something a value, it will remember it until we change that value. And we're not saying assign N1 equals 0, because that would connect it to ground. We're saying N1 and then this funny arrow, which is a less than followed by an equal sign. It's saying load a 0 into this variable N1. And N1 is basically a flip-flop. Okay, so we say register N1. Usually that means N1's a flip-flop. It can remember a value. And down here we're just going to say let's load a value of 0. And so now if we look at the value of N1, it's going to be a 0. But later on, if we say N1 gets assigned a 1, then if we look at N1, it's going to be a 1. Okay, so hold that thought, because this will make more sense in a second. So N1 and N2 are registers instead of simple wires. Out is a wire. And we have our usual assign statement, which says take N1 and N2, feed them to an AND gate, take the output, connect it to out. Okay, that's our whole AND gate, but we want to put values on the inputs, we want to look at the outputs. So we're doing something here which is not synthesizable. What we put in this part of the module is not something that gets turned into hardware. These are instructions that can be used to simulate the behavior of our circuit. So we got to kind of get a little two-sided here in our thinking of this. The first set of code, that synthesizes into a piece of hardware, an AND gate in this case. When we say initial, we're listing things that we want to have happen when we start simulating this. They're kind of initial conditions. Okay, so we say initial, and we're doing a bunch of things. So we're going to start with begin, and we're going to end with the keyword end. And everything in between, that's what we want it to do. So the main thing we're going to do is we're going to assign values to these registers. So initially we're going to assign zeros to N1 and N2. And these things, number sign 10, that's saying wait. This is saying wait 10 nanoseconds. So we're putting in some time after we set the inputs to let the circuitry do its thing. And then we're going to set input 1 to 10 nanosecond to a 1, and we're going to wait 10 nanoseconds. And then we'll set input 2 to a 1 and wait 10 nanoseconds, and so on. The other thing we're doing is this display statement, which says something like printf. It's saying while you're simulating, when you get to this point, print out a message that says N1 equals, and show me the value of N1, N2 equals this, X equals this. This is a printf from C. It's clearly not something that's going to be synthesized into hardware. Right? This is just an AND gate. There's no printing, there's no screen or keyboard or anything like that. This is something the simulator will use. You had a hand up.
Do you have to put wait time?
You don't have to, but if you're changing an input and you want to look at the outputs as a result, throw some wait time in, because these things do take time. I threw a lot of wait time in here just because I wanted to sort of do one thing per step, just for the sake of example. We can also print out messages like display hello. And this is useful because what we're going to do is we're going to use this test bed to set inputs and step through time, and this is going to generate a bunch of output. Well, we might want to put some messages in there to tell us what we're doing, so that later on, after we've simulated this, we can look at all the output and say, okay, here's where I started doing this test, and here's what the outputs were and the inputs and so on and so forth. So all of this is working on this synthesizable circuit that we basically created here, but this is kind of a simulation language from this point down. So we can assign values, we can create delays, we can do display statements, and we can substitute in the values of variables by using this %d notion from C's printf statement. And we can also say, I want to create a file in my directory that has all of this information in machine-readable form, so that I can do some further analysis on it. So that's what this dump file does. It says I want to dump all of this information into a file, in this case called test2.vcd. And then dump var says go ahead and dump all the variables into that file. And so as it's running, every time that a variable changes, it will write a new entry into this file recording the new values of the variables. And we'll see how to analyze this file in a minute. Okay, so that's pretty much everything in here. $finish says we're done with the simulation. That will close everything out. This end goes with the initial statement, so that's the end of our initialization, and then end module is the end of the module. So if that made some sort of sense, that's good. If it made very little sense, that's not surprising. But you can kind of use this, right, or the things in the handout, kind of as a template, right? And you can change your actual Verilog if we do this to simulate an AND gate, and now you want to practice, turn this into an OR gate. Assign out equals in one pipe in two. Or make it an inverter, out equals exclamation mark in one, right? And play around with it, get some practice doing this. But let's go ahead with an AND gate. Okay, so this is just a plain text file. This is called test2.v. V is the extension for Verilog usually. And to compile it, you use the iVerilog command. Okay, so on Collaboratorium it'll be C:\Icarus /iVerilog, right? Or set up your path variable if you know how to. So let's compile this. So I'm going to compile it. I'm going to send the output of the compilation into something called test2. That's a.out if you don't specify it, just like GCC. And the program I'm compiling is test2.v. So I do that, and it creates this test2 file. And we can read it, but it's not very fun. Right? This is really meant for computer use. But that's basically a description of your circuit and of what you want to do to simulate it. So it's taken our Verilog code, which is human readable, and it's turned it into this, which is machine readable. Now if I say VVP test2, that says go ahead and simulate our circuit and our test bench. And when we do that, it tells me that it's set up test2.vcd as a dump file. We said display hello, that's where it displayed hello. And each time we said display in1, in2, and x, it generates one of these lines. So in1 and in2 were 0, x was 0, when 0 was a 0. When they were both 1, x was equal to 1. And when it was 0, 1, x was equal to 0. So it looks like this is a viable AND gate, just based on these simple tests. Okay, last thing, you want to look at this graphically, we use something called GTK Wave. So GTK Wave, and I'm going to feed it whatever this dump file was, test2.vcd in this case, and it opens up this graphical window. And it's really tiny up there, but over here it says test bed. If I click on that, I see all of my signals. I have a register in 1, register in 2, and a wire out. I can take these and drag them over here where it says signals. And let me make this a little bigger. And everything is red here. Red means it's undefined. But if you look at the time scale up here, this is 7 picoseconds over here. So I need to scroll way the heck over to get to where anything useful has happened. Okay, so it's very, very zoomed in right now. It's looking at a 7 picosecond window of time, and our simulation ran for a few hundred nanoseconds. So if you want to zoom out all the way, there's a button over here, zoom fit, click that. Now we've got a timing diagram for the simulation we just ran. So over here, about 12 nanoseconds, our input and outputs got real values. In 1 and in 2 are both 0, and I can click anywhere I want, set a cursor, and it'll show me what the actual values are. So in 1 is 0, in 2 is 0, out is 0. Over here, in 1 changes to a 1, in 2 is still 0, and the output is still 0. But over here, both my inputs are 1 and the output went high. And then over here, I dropped the first input, left the second input high, and the output went low. That's an AND gate. So it's generating these timing diagrams for me based on that simulation. Yeah?
Is Verilog susceptible to
glitches.
Propagation delay?
Yes. And we can actually enforce propagation delays. We can put in deliberate propagation delays to see what happens. So if we know that one thing has a certain delay and another thing has another, we can actually say, set the output equal to this after 2 nanoseconds. And we can generate timing diagrams that will actually reveal glitches to us. And when we're using the full-blown FPGA software, right, we're still putting in Verilog, but the FPGA software is a lot more complex. This is basically 3 steps: compile, execute, look at the results. The FPGA stuff will run through dozens of steps, and it'll do things like timing analysis and glitch analysis and power analysis and all sorts of things like that. All right, well, let's change this. Let's make an OR gate. So that's all I got to change. Just change that one assignment statement. But I got to actually change it. Okay. So I can say iVerilog, I can say VVP. I can look at my output and I see that every time that either N1 or N2 was a 1, the output X was a 1. So that looks like an OR gate now. I can rerun GTK Wave. I can drag my signals over here. I can zoom out. There's your OR wave. So here's the output, and it's high as long as either or both of the inputs is high. So one of the buzzwords here is rapid prototyping, right? We just completely changed from an AND gate to an OR gate and it took about 45 seconds to rebuild the circuit, compile it, execute it, get up some timing diagrams. And if you build a circuit and it doesn't work quite right, you've got timing information, you've got output that you're printing, usually it's pretty straightforward to figure out where the problem is, or put in more display statements to narrow it down. And, oh, I meant to do B and I did Q instead, right? Go and change your code, redevelop it, compile, simulate, look at the output. So let's make an adder. We're done. There's an adder. It's a 2-bit adder. I could make it a 4-bit adder. I could go 3:0, 3:0, and 4:0. But how are we going to test this thing? It's a little trickier. So here's what we're going to do. I'm just going to make some different test cases. So I'm just going to give N1 and N2 different values. I'm going to start them off both at 0, and I'm going to just wait 10 nanoseconds. I'm going to display what the input and output are. And then I'll set them both to 1 and display the output, and then 1 and 2, 2 and 2, and so on. So just some different inputs for A and B. So this is where your test plan would come in, right? You're supposed to develop a written test plan. So how would you test a 2-bit adder to see if it's really a 2-bit adder? Well, maybe you go through every single possible combination of inputs, but what about a 10-bit adder? 2 10-bit numbers. To do every possible combination of inputs would be 1,000,000 tests. And that's probably not what you want to do. So you come up with a set of tests that you feel if you pass those tests, your circuit is working correctly, and you can code those into this initial block in Verilog. And this is nice because if you want to make a change to the circuit, right, you change your code up here in this area, and you can use the same test again and again, right? And in the way that this is described in the handout, these are actually broken into separate pieces. There's one file that describes the circuit you want to test, and then a totally separate file that's actually the test bench itself. And the test bench just includes your circuit inside it. And then you're really just writing a bunch of input vectors and ways to look at the output. So let's try this, right? We set the output to the sum of in1 and in2. We'll compile it. We'll execute it. And does that look like a good adder? 3 plus 3 is 6. 3 plus 2 is 5. I think that looks good. So let's look at waveforms. And let's zoom out. And yeah, my input is 1, 0 on input 1. Input 2 is 1, 0. That's 2 plus 2. And my output is 1, 0, 0, which is 4. That looks like it's doing the right thing. So this is treating both of those input 1 lines, bits 1 and 0, as a single signal, and it's showing me the binary version of it. So 1, 0, 1, 1, and so on. If I double click on this, I can see each of those individual signals. So here's bit 0, here's bit 1. And on my sum, here's bit 0, bit 1, and bit 2. So there's a nice, big, complex timing diagram for a 2-bit adder in a series of test cases. And you can print that out and stare at it and see if it's right and mark where it's wrong and so on. Making some sense as far as kind of the general flavor of what working with Verilog is going to be like as compared to working with a proto board, working with an oscilloscope, things like that. Right? It's all software. It does a lot of the heavy lifting for you. And so it makes it a lot faster to go through iterations of your design.
Are you able to like generate an error and then walk us through what that would look like?
Sure. What sort of error should we make?
Anything?
So the first thing is compile errors, right? So let's say we forget a semicolon, right? Well, that's pretty straightforward. So it tells me test2.v is the file, colon 11 is the line number it's stuck on, and it's saying there's a syntax error there. So with C, with Verilog, with any of these things, my suggestion is always look at the first error message, ignore everything else. Because sometimes you have one error and you get 500 lines of error messages, right? And the ones that you see at the bottom are the least important. It's the first message you really want to think about. So don't worry what invalid module item means. I have no idea what that means. But let's look at the first message, syntax error on line 11. So go back into your file, come down to line 11, and it's complaining about wire 2:0 out semicolon. It thinks that's a syntax error. Well, it's clearly not, right? I've told you that this is a valid statement. But if it's telling you there's a problem here and you don't think there's a problem here, there's probably a problem close to that. And it's probably on an earlier statement. So now you look at the statement right before it, and you say, hey, there's no semicolon here. So it thinks this statement is register 1:0 into wire 2:0 out semicolon. It thinks that's one statement, and that's not valid. And it's because we didn't end this statement with a semicolon on line 10. All right, so go up and fix that. Okay, so we call our output variable x instead of out, which is a mistake, and we compile it. Wow, it actually compiled. That's weird. Okay, let's go with it. Let's simulate it. Oh, x, okay. So we simulate it, and n equals 0 and 2 equals 0, but x is equal to z. And that's a little weird. So let's look at this in our waveform. And let's zoom out. And in 1 and in 2 seem to be going through the different values that we wanted. That's those first 2 traces. And X is taking on values of 1 or 0. And we expected a 3-bit output, but X is just a single bit. And we've got this other output here, which is 3 bits and never seems to have a valid value. It always says it's just equal to ZZZ, right, which is undefined. And so you scratch your head over that for a while, and you go back and you look at your code, and hopefully that leads you to the idea that, hey, I'm not doing anything with my output. I'm not giving it a value, right? So go back into your code and search for out. Well, that's where I give out its declaration as a wire, and I display it, but I don't do anything else with it. I never give it a value. And eventually you come down here and you say, oh yeah, I'm assigning to X instead of out. I really wanted to set out equal to that. So debugging is not an exact science, right? It's really another art form, like programming. It's one of the 3 pillars of programming in my book. And when you work in a different language or a different paradigm, Verilog, something object-oriented, a functional language, right? Your debugging skills have to get developed for that particular framework. And it's a trial and error thing. And in the beginning, it can be pretty laborious, right? But I'm always happy to help people debug their code. Okay, it doesn't mean I'll look at it and tell you where the problem is, but I'll help you use whatever tools are available to look at it yourself and find where the problem is. Okay, and that's a big part of learning this stuff, is learning how to debug. So if you're having problems, right, definitely shoot me a note or come by if I'm here, and I'll help you figure out where the problem is. So other questions? Like I say, if this is not crystal clear, that's perfectly normal, okay? I should give you this disclaimer up front. It took me about 2 years for this stuff to click for me. Okay, for about 2 years I looked at Verilog tutorials, I read things about Verilog, I looked at code, just didn't make any sense, right? Went back to it every probably 4 to 6 months and tried again, didn't make sense. Finally, after about 2 years, I went back to it one day, started looking at it, and it just like clicked. And I think when that happened, then I sort of like went to the other side and I lost the ability to explain why it is that it wasn't clicking and what it is you need to know in order for it to click. So it may not take you 2 years, okay, but it may not click right away. And that's okay. It's a different way of thinking. But for me, the biggest conceptual leap was really this idea that you're describing hardware as opposed to describing an algorithm. And I think that was the thing that finally sunk in after multiple tries that made it possible for you to sort of start working with this stuff. But you can take this kind of thing, right, and just start running with it. We haven't gotten to section 6 yet. We'll touch on it, but we're mainly going to do this on Tuesday. But so far we've been doing this stuff up through section 5, and mostly culminating in section 5, which is behavioral Verilog. But then down here, section 7, we talk about doing simulation, and lab 7 also talks about this. So this is this idea of having an initial block. Where's my initial block? Initial. And setting values to inputs and displaying outputs. All right, so the lab talks you through using the stuff from a command window. So on DOS, right, hit the Windows key, hold it down and press R, and then enter CMD, and that opens up a DOS prompt. And you can use Notepad to edit files. So Notepad space file name will give you an editor, and then you're just going to use C:, iVerilog. I'll double check that stuff. But like I say, give it a try and grab me. And then try to put this code in and simulate it. So there's test bench code here. So you don't have to write any Verilog for experiment 1. It's basically reproducing what we've been doing here. But that gets you to using the tools, gets you to where you compile, run, and look at output using GTK Wave. Icarus Verilog, by the way, is totally free, right? It's an open source Verilog system, so you can download it on your own equipment and use it as you like. There are commercial versions of all of this stuff, some of which are free but require a license. That's what we'll use for Lab 8. Some of which can cost you, hundreds of thousands of dollars, depending on the quality of the software. So we're using a free one. So it works well, but it doesn't do all the bells and whistles that the $300,000 packages will do for you. That's fine for what we're doing. The real issues come when you're trying to build a circuit that has, maybe 50,000 gates inside it, and you're trying to put it on a device that has 60,000 gates available, so you don't have a whole lot of room to work with. You really want to somehow use those gates very efficiently, so you want to do a lot of minimization, right? Come up with the fewest number of gates, but you also need to know what kinds of gates are available. If you've got a lot of AND gates, and your design really only uses a bunch of ORs, you'd like to do some De Morgan and change some of your ORs into ANDs, for example. Or maybe you're worried about timing. Maybe you want to make sure that this circuit can run as fast as possible. Or maybe you want it to take the least power possible. Or maybe you want to minimize the difference between the longest propagation delay and the shortest propagation delay from input to output. These are all knob settings you can set on the fancier software. And this is where your compile step can go from a few seconds to 3 or 4 days. So it's an interesting world to work in. And it's a world that you can make really good money in. If you're really good with things like Verilog or hardware definition languages in general, and if you're really good with particular tool chains, and we're going to work with a chain from a company called Xilinx for Lab 8. If you've got those skills and that experience, right, you can walk into a really nice position out in the valley. Because it becomes kind of an art form. Because you have to understand the tools and understand what they're doing and know how to sort of like nudge them in the right direction sometimes. And it's something that just comes with years of experience. So you can go on to LinkedIn or places like that and look at job listings and see some really good 6-digit salaries for FPGA designers, or people doing design work on FPGAs. So the stuff we're doing shouldn't be too wacky, right? It should work pretty much perfectly when you get it written correctly with the tools we're using. Lab 8, it'll get a little more crazy. So you probably have enough to do experiment 1 and experiment 2 on Lab 7, right? Not immediately, but to take some of the stuff we've been doing and type it in, right? Make yourself a file, try to compile it, simulate it, and so on. And when you're at the point where you can do those mechanical operations, right, you should be able to do experiment 1 and experiment 2. Experiment 3, we're going to have to talk about a different aspect of Verilog, which is a whole nother can of worms. But we can start it for a few minutes today, and then we'll mostly talk about it on Tuesday. But questions up to here? And this is one of those things where it's hard to have questions until you figure out more of the answers and then figure out what's not clicking. Yeah?
Do we have like a cheat sheet of just quick commands for Verilog?
There's tons of them available, but I would stick with code samples in this handout.
Okay.
Right, so this one I keep looking at is Intro to Verilog Programming. It's in the lab section right after Lab 7. It's a PDF. And all the code that you should need to do is found in these samples, right? Plus a whole lot more. And that's really the best way to sort of nail down, do I need a semicolon after I say module or not, right? Well, there's sample code here. If you have these compound statements, you can mark them with begin and begin and end don't get semicolons after them for whatever reason. So things like that. So the other part of Verilog, which is where it really gets crazy, is when we talk about event-based Verilog. And this is where we move, because everything we've done so far, we're basically describing combinational circuits. Right? Here's the inputs, there's the outputs, this is how we change inputs to outputs, assign statements, ternary operators. Those are really combinational circuits. They're things we could describe with a truth table. A 10-bit adder, it's just a big combinational circuit. So it gets more interesting when we start talking about event-based behavior. These are sequential circuits. These are circuits that have clocks and whose behavior depends on what's happened in the past. And Verilog has mechanisms for describing event-based circuits, things like state machines. And we can describe state machines very easily using this language. We don't need to make a state diagram and turn it into a transition table and write equations and all of that stuff. Okay? That would be a structural approach to making a state machine. We're going to stick with behavioral methods. So we're going to say, what do we want our system to do? When the clock ticks, what should it do? Well, if the state variable is currently 1 and the input is 12, then I want you to set the output equal to 3 and go to state 7. And we can basically write a Verilog statement that says that. And we do that for all the different situations that we might encounter. We compile it up and it'll build a state machine for us. And the whole key to event-based behavior is going to be this always statement. So we're going to have these things called always blocks. And they're usually going to say always at the positive edge of a clock. And we'll describe what we want to have happen when the clock ticks. So we'll do that on Tuesday. And this will really open up a huge swath of design landscape that we can go through pretty easily with a little bit of Verilog. All right, parting questions. Yes.
Are we gonna mess around with the part where it builds an entire circuit for us? Well, for one, and then two, is there a way for us to look at it?
Yes. So so it is already building an entire circuit for us, right? Even if it's just an NAND gate or a 2-bit adder. But when we work with the Xilinx software tools, Lab 8, after it's compiled our design for us, we can actually say, show us the circuit. And it'll actually show us a schematic for it. And we can also say, show us the equations, and it'll show us the equations. We can say, show us the truth tables, and we can say, show us the K-maps you used. And it'll make all of that available for us. So I'll post a link to that video, and we actually touched on some of that at the end of the talk on Friday. And I showed this I picked on a 2-bit adder in that talk, so went through it, but using the Xilinx toolchain instead. So, all right, I'll figure out where exactly these things are on the collaboratorium, and I'll post that in a note along with a link to that video, and then just come and hit me tomorrow if you've got questions on this.
You said you'll be here what time?
I've got office hours at 9 to 10, and then from 11 to 12, and I'm in here from 10 to 11, but I'm not lecturing. So you can come in here and ask questions. Yeah, I'm basically just here for students in 223 to work on their stuff and ask questions.
So you said that the software storage?
So